So we are looking at a situation where we've got a p-value of 0.045, a significance level is 0.05. So according to this, we would, at this point, we would choose to reject the null hypothesis because according to our p-value, it is unlikely that this would have occurred by random chance alone at a significance level of 0.05. Now, in reality, there we go, we do have the calculators. In reality, the null hypothesis was actually true, but we rejected it. So this is an example of, it is an error, and I will tell you that, well, that's all I'll say. So it is an error, so which one is it, type 1 or type 2? If it's not type 2, what would it be?
Type 3. Type 1.
There we go, we heard it, type 1. All right, so there you go. Type 1 error is the case here. So we rejected the null incorrectly. So we rejected that there is no wolf, going back to our story time yesterday. So the null is that there is no wolf. We rejected that. In reality, there was no wolf. So we committed a type 1 error. Okay.
Wait, but since you're
Let's see what we got here. We've got some activity fun. We've got some, look at this. We're going to find out how to conduct a hypothesis test for means. We've only done it with proportions. So this is a good question right here. We learned a little bit about one-tailed versus two-tailed test. It says one-sided or two-sided, but same thing. One or two-tailed tests and what the hypotheses would be. Let's not worry about writing out the hypotheses. Maybe we can do it for one of them, but just looking at this real quick. A college dining service conducts a survey to see if students prefer plastic or metal cutlery. And do you think this would be one-sided or two-sided? I like those options.
Can you define one-sided and two-sided again?
One-sided basically means if you have an idea that the change or the difference trends in one direction, like the null is that these are equal. The alternative is that there's a difference and this one is far more, way more preferred. Or if there's the null is that this particular drug has no effect. And the alternative is that this has an effect that decreases the amount of incidence of this disease, right? So that would probably be an example of one-sided in that case, because we already have an idea this drug, this new proposed drug, maybe has an effect that will reduce the incidence of this disease. So we're only going to check it one way, make sure it's less than the established level. Mm-hmm. Yeah. Yeah, and yeah, two-sided would say it could increase or decrease, and we just don't know the direction it's going to go. Ideally, a drug doesn't increase the prevalence of a drug. Now, I would say for this first one, do we have a sort of an idea of which one's preferred, plastic or metal? No. So maybe this would be appropriate for what kind of test? Two-sided. And this would actually be an example of perhaps a test that we don't know how to conduct yet. This might be a two sample z-test for difference in proportions, and that's going to be something that we look at in chapter 10. So we're not trying to come up with that, but we could frame some hypotheses different ways. All right. In recent years, 10% of college juniors have applied for the study to study abroad, whatever. The dean's office conducts a survey to see if that's changed this year. Does this seem like a one or a two-sided test? Okay, why do you say two? There you go. So there we go. And I thought that was well put. It could have more or less. And sometimes the phrasing of it itself will tell you if it's a one or two-sided. Right here it just says, has it changed this year? Well, change can go in either direction. So that's fair to call that a two-sided. All right, let's just jump down to the last one, though you can tackle that third one on your own if you want. At a small computer peripherals company, only 60% of the hard drives produced passed all their performance tests for the first time. Management recently invested a lot of resources into the production system and now conducts a test to see if it helped.
One said they want to see production for more past that.
There we go. So according to the prompt here, we have an indication that we're only interested to see if that number's gone up. That would be pretty awful if you maximized your process and then went down in quality. Okay, so yeah, this would be one-sided. And so just to write this one, and then we'll move ahead. The null hypothesis is that, let's see, the proportion is what? And we're looking at this part D. 0.6. So we're using the baseline. We would say all of this optimization they just didn't have an effect. That's our null hypothesis. They still only get 60% success the first time. The alternative would be what? Greater than 6. We think that this has improved the quality of the process, and therefore we should see higher than 60%. There we go. Okay. This is an interesting concept right here. This goes into type 1 and type 2 errors. So I think it's worth it to spend a little time talking about this. So I know it's a couple, it's like reading a passage on your ACT, but anyways, spam filters try to sort your emails, deciding which ones are real messages and which are unwanted. One method used is a point system. The filter reads each incoming email and assigns points to the sender, the subject, keywords in the message, and so on. The higher the point total, the more likely it is that the message is unwanted. The filter has a cutoff value for the point total. Any message rated lower than the cutoff passes through to your inbox. The rest, suspected to be spam, are diverted to the junk mailbox. We can think of the filter's decision as a hypothesis test. The null hypothesis is that the email is a real message and should go to your inbox. A higher point total provides evidence that the message may be spam. When there's sufficient evidence, the filter rejects the null, classifying the message as junk. This usually works pretty well, but of course, sometimes the filter makes a mistake. So the questions: when the filter allows spam to slip through into your inbox, what kind of error is that? Well, let's not answer that just yet. Let's go ahead and write down our null hypothesis. What is the null hypothesis for this spam filter?
Email is a real message.
All right, it's a real message. And the alternative is that it's spam. So sometimes it's good to just write out your two hypotheses rather than try and hold that information in your head. All right, so now we can look at this. When the filter allows spam to slip through your inbox, first of all, did it reject the null hypothesis or did it fail to reject the null hypothesis? It failed to reject it. Yeah, and so let me clarify. When we're saying that the null or the alternate hypothesis is that it's spam, we're not saying in reality it's spam. We're saying it's been decided by this algorithm that it's spam. Now, if a spam message is determined that it's a real message, then that is an example of failing to reject. So we failed to reject the null when we should have. So is that type 1 or type 2?
The other one.
It's yes, okay. Type 2. Okay.
I kind of get my notebook out.
So, and again, this might or might not be helpful. These might be the kinds of problems where you need to actually take a minute of just thinking. There's no math going on the paper, but you're just sitting there thinking and whatever you need to. But whatever the case, if you think about the boy who cried wolf, the second instance, the townspeople failed to reject the null hypothesis. They should have rejected the null that there was no wolf. They should have decided that there is a wolf. They failed to reject it. And so therefore they made a type 2 error. All right. Again, that's the best mnemonic I've ever seen for type 1 and type 2 errors. Otherwise, you just have to kind of think through it and hope you got it right. All right. So as far as this goes, this is a type 2. What kind of error is it when a real message gets classified as junk? There we go. Hopefully this one's pretty straightforward. But here's what happened is they rejected the null hypothesis when they should not have. It was a real message. It should have been accepted as a real message. But instead, they rejected the null hypothesis incorrectly. So that's type 1. Okay, some filters allow you to adjust the cutoff. Suppose your filter has a default cutoff of 50 points, but you reset it to 60. Is that analogous to choosing a higher or lower value of alpha for a hypothesis test? And I want to rephrase the question. When you raise it from 50 to 60, is it easier or harder to reject the null hypothesis?
It's harder to reject null hypothesis because more spam gets through.
Okay, so we made it harder to reject the null. So let's say that the 50 corresponds to a 0.05. Through analogy, did we just make if we've just made it harder to reject the null hypothesis, did we just make this alpha level lower or higher?
We made them all
Lower. That's like moving from a 0.05 to 0.01. I'm just making up numbers. I'm not saying those numbers actually correspond. But when we go from an alpha significance level of 0.05 to 0.01, we're saying that we want to have it be really, really extreme p-value in order to reject the null hypothesis. And by the same token, when we take this 50 cutoff and we raise it to 60, it has to be really, really obviously a spam message in order for it to be classified as spam. So it's harder to reject the null and to classify something as spam. All right. So when we changed this cutoff value, how did that affect type 1 error? Did that make the type 1 error probability go up or down?
down.
There you go. And this is something we talked about yesterday. I know it's a lot we talked about yesterday. But through analogy, if we went from a 0.05 to 0.01, then we just reduced the probability of a type 1 error. But by the same token, we just increased the probability of a type 2 error. Okay. And that is something that we will get into. That's not going to be today. That'll be Monday. All right. So good to talk about that stuff. And hopefully you're looking through the homework so you can get some more practice with it. Certainly feel free to stick around. If you are looking through the homework regularly and there's some of them you don't know, you don't have to just look at the answer in the back of the book and try and reverse engineer that to figure out what you're supposed to do. You can show up to class and hang out after and say, let's look at problem number 19. And then we can look through that one. Okay. So, I want to make sure we have enough time to cover our content today. I will say this, if you want to come back to type 1 and type 2 errors and we can talk more about it, we can do that tomorrow, or not tomorrow. We can do that at the end of class today, or, whatever, however we want to return back to that. So teenagers, here's our activity for the day. We're now jumping into our other content. Teenagers are supposed to get 8 hours of sleep, but I doubt you do. Maybe I'm wrong. Let's record the number of hours you get of sleep you get per night. There we go. Now, okay, let's not do that. Yeah, go ahead and mark on the screen and put how many hours, just best guess. Per night, how many hours per sleep you get.
Should I actually just choose one instead of doing random?
You can, let's not make it like too precise, but if you think you get 7.5, put it at 7.5. Yeah, don't be like, I get 7.25 hours of sleep. No. Okay, that's, I see 1, 2, 3, 4, 5, 6, 7, 8, now 9, 10. And then waiting for the 11th. I will put my own dot up there. I'm not a teenager, so I can't join in this. I'm not.
Hours?
All right, let's go with this. I think I'm only seeing 10 dots. 1, 2, 3. Oh, there we go. 1, 2. Is that at a 5, Aries?
Yeah, it's like 5.
Okay. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I believe that's everyone. Now, we don't need to worry about a distribution on this. That's not a big deal. Let's just go ahead and calculate the X bar and sample standard deviation. Okay, we do not want to calculate this by hand. So you might want to put this into a list and let your one variable stats handle it from here. So having our numbers now, we're going to test to see if you really get the recommended 8 hours of sleep every night. And the first question, are we working with proportions or means? We are working with means. We're looking at the average of all of the sleep, the sample mean, and we're going to see if that is, what am I trying to say? We're going to see how that compares to the average that you're supposed to get. So let's write some appropriate hypotheses. What would our null hypothesis be for this?
That we do get the recommended sleep.
All right, and how can we put that in the form of a hypothesis in like statistical notation?
Null hypothesis equals 8.
Okay, equals 8. What equals 8 here?
The true mean.
Ah, true mean, mu. So it's important, and this is why we define this at the beginning, because just saying mu equals 8 doesn't necessarily mean anything.
No, true.
So we could say, what did I say?
You said mu equals 8. And I said, no, u equals 8.
Okay,
Ah,
got it.
the knee slapper.
All right, so mu here is the true mean hours of sleep for teens. And now there's no doubt about what that means when we say mu equals 8. Now the alternate hypothesis is what? Greater than, less than, or not equal to? Not equal to is a more conservative estimate. Are we concerned that high schoolers are getting more than 8 hours of sleep?
No.
No one's concerned about that. All right. So in this case, like I was saying, if you did do not equals to, you would get a more conservative analysis, and if it was still statistically significant, it would definitely be true that something was up. But anyways, it's pretty safe to say we're only testing one direction. Oh. So the conditions here, let's run through what conditions do we have for significance tests?
Randomness.
It has to be random.
It's not random. This is our stats.
I know we might fail at more than one of these. Ah, there we go. We have to make sure it's normal. It's means, so we're looking at, there it is, central limit theorem.
And we gotta make sure that less than 10% of the population.
There it is, 10%. So which one of these do we definitely qualify for? 10%. Yeah, you guys do represent less than 10% of teenagers. Maybe if we're looking at egos, you account for more than 10%. But all right. Now, random, this is not a random sample. We're going to understand that that's not really met, but we're just going to move forward. You do know what you're looking for when it comes to a random sample. Now, normality here, because we're dealing with means, we can't use the large counts test. And what we've got to do is if our sample size is greater than or equal to 30, we're good. We haven't met that. Now, the next one is the population that we're drawing from a normal population? Do you think that hours of sleep is approximately normally distributed among teenagers?
There's probably a skew, but
There might be skew. Yeah.
I'd say it's pretty good.
Yeah. Maybe it's fair to say that it's approximately normal. So if we decide that the population would have this kind of a distribution, maybe centered around 7, I don't know, whatever but if you feel like you're gonna have some people who get like 0 hours of sleep up to people who might get like 14 hours of sleep. Now, I don't know that those numbers are realistic, but still, those are out of the extremes. Anyways, if that seems like a realistic distribution to you, you can justify it. You can have a comment to that effect. You could say, it seems likely that the population we're drawing from is normally distributed. Therefore, our sample should be our sampling distribution should be approximately normal. So that's the other one. So and you could just say population is normally distributed. So we actually did meet 2 of our 3 conditions. This is not random, so we wouldn't ever actually use this, but you guys have the idea. So the formulas for the mean and standard deviation of a sampling distribution for means, you don't have those memorized most likely. So that's why you have your reference sheet. So you want to look up first of all, we're looking on the back of the front page, talking about sampling distributions. We know we're dealing with means, so that's going to be in this box right here. And we're dealing with one mean, so we're going to be looking at these formulas right here. The formula for the mean and standard deviation of sampling distribution for means, well, if we're looking at the mean of means, what does that equal to? There, I just put it on the screen. I mean, this is literally on this formula sheet. I know, it's a burden to get that. Okay, well, I would recommend having, I'm guessing you had the formula sheet the other day and not a calculator. So you have it today, you have a calculator, not the formula sheet. So one of these days, we'll put it all together. All right, now the standard deviation. Now, and of course, you're probably already thinking, well, wait, this is not a true sampling distribution. We're looking at a hypothesis test. So this is what we would normally have. But of course, we're dealing with not population data, we're dealing with sample data. Okay, so what will our sampling distribution mean and standard deviation be? So we're going to go with the best estimate we have for the standard deviation is going to be our sample standard deviation. So the standard error, I should say, for the sampling distribution here is going to be our sample standard deviation divided by the square root of n. Now we're going to go ahead and use, for the mean of our sampling distribution, it's going to be the mean of our null hypothesis. So it's going to be the 8, right? So that's not a notation that we formally use. I'm just showing that this is a mean that comes from our null hypothesis. So our mean is 8. We don't have any population estimates on the standard deviation. So with this, we had our numbers. Let me pull it up again. It was 1.4424 divided by the square root of, we had a sample size of 10. All right, so I got 0.456. All right. Are you guys good with this so far? Okay. So we want to find our test statistic based on this. So we want to draw a picture. I'm going to go ahead and get rid of the formulas right here. And that was just to remind you of what formulas we're working with. But of course, we are really working with that one using the sample standard deviation, or sample standard error and all that fun stuff. I can't talk right. Sampling distribution, sample error. Okay, so we've got a sampling distribution, and we think that this is going to average out at 8. Our actual mean, I forgot, it's like 6.45. I have to pull it up again. 6.45. So X bar is 6.45. And the standard error here is 0.456. All right, so this is going to go at the first standard error way, it's going to be 8.456. At the first one down below, it's going to be 7.544, and then so on. So 6.45 is going to be somewhere around here, I'm guessing. So 6.45. That's down pretty low. If the null hypothesis is true, that's pretty low. It's pretty unlikely. All right, so we can calculate this. So the normal test statistic is that it's the stat minus the parameter all over the standard error. In this case, we are going to end up with what's called a t statistic. And the stat for us is 6.4. Well, actually, I don't want to plug numbers in yet. It's going to be our X bar. Nope. Didn't erase enough. There it is. X bar is our stat. Mu is the parameter. And now it's going to be S over the square root of n. So this right here represents your test statistic. And notice when we did it for proportions, it was a Z statistic. Now it's a T statistic, and we're going to come back to this. This distribution is not a Z distribution, it's a T distribution. I mean, that's going to have important effects when we do our calculations at the end. Okay. So at this point, I'm going to plug numbers in. My test statistic is going to be 6.45 minus 8 divided by 0.456. And you guys can do that math. So negative 3.399, if you save the exact values from earlier, you're going to be a little bit different from that. But yeah, negative 3.4 essentially. And we can see where that is over here. I didn't go quite far enough out. but we're looking to see what's the probability of a sample of 10 people getting that value or lower, assuming that the null hypothesis is true. And we can already know, are we going to reject or fail to reject the null hypothesis?
Yeah.
We're going to reject that, but we need to make sure we reject it the right way. Just like other situations in your life. Make sure you reject people the right way.
Yeah, you can write them a letter.
Yeah, you can do it in a group chat. Okay, so let me clear all this. We have our test statistic, and we're not, okay. Because we're working with means, our test statistic is not a t-value, but a z-value, but a t-value, and we have to consider the degrees of freedom. Okay, and we have two methods for checking the p-value when we're using a t-value as a test statistic. All right, here's method number one. We can go to table B, and this is on this paper that some of you have. And this is going to get a little bit strange, but let me see. Do I explain it here? Okay, I'll just explain it, and then we'll have it like laid out. This is, in case you look back at this presentation later, it has the process laid out. But first of all, we need to figure out our degrees of freedom. How many degrees of freedom do we have in this? 9. Remember, it's degrees of freedom equals your sample size minus 1. So we have 9 degrees of freedom. I'm going to look at this row right here. And I want to find on this row where my test statistic is. And we will not find our test statistic, right? But as I go across, notice 0.703, 0.883, all the way over, the negative 3.4. And don't worry about the negative. That's going to live somewhere right here, right? It's going to be between 3.25 and 3.69. So with this, I can tell you the p-value. Let me write it this way. P-value has to fall between those two values. It's got to be less than or equal to 0.005, but it's got to be greater than or equal to 0.0025. Now we can already see those. That's incredibly small for a p-value. I don't know. I can't tell you anything more accurate than that. So on a B table, but I'll tell you this is also good enough. Because remember the AP test is designed to be done without a calculator if needed. If you had to do this by hand, that's what you could do and you're good to go. All right, is everyone good with this so far? All right. So this, let me see. So I'm not going to run through this. This is a hypothetical. We just ran through it and we found our p-value is going to be between these two. Now I want you to remember those. It's going to be between 1/4% and 0.5%. Okay. And in that range, we've already decided what our significance level is. We would choose at this point to reject the null hypothesis. You guys do not get 8 hours of sleep at night. That's safe to say. Now, the other method is to use your calculator. And let's remember what we narrowed it down to so far, and let's narrow it down even further. Just like we can calculate the area under a normal curve with normal CDF, we can do the same thing under a t-distribution using t-CDF. How about that? So if you go into your distributions, you can, so we need to know how to use table B, but I want you on your calculator to go to second in distributions, and you're going to find t-CDF. It's option number 6. I think I run through it right here. Now we want to put in, so if you select that, if you're following along, we have a lower or upper value for this. So here's just a couple things to remember. Our t-value is negative, right? Negative 3.4, and we can just call it negative 3.4. So we're looking for that value or lower. So is negative 3.4 going to be the lower or the upper bound? Upper bound. So yeah, we're going from negative infinity to negative 3.4. Now we also need to plug in the degrees of freedom. All right. So our degrees of freedom, we decided was 9. And the number I got was 0.0039. And this is good. This confirms what we did on the table B, because what we were able to say is that it was going to be between 0.0025 and 0.005, and that falls between it. So at least at the beginning, maybe it's good to see it both ways so we can confirm that both of them work adequately. All right. But the TCDF is pretty straightforward. If you have access to a calculator, and everyone should, there's no reason not to use that. There's no reason the test I can think of that they would force you to use table B. But there you go. All right, any questions on this? Okay. So here you go. You can see I put the test statistic in the corner. We call this a one sample t-test for mu. So just like we had a t-interval when we did our confidence intervals, we have a z-interval, t-interval, z-test, t-test. And we know which one to use because there's always a z-test using normal calculations for proportions, a z-test, z-interval. If it's means, it's always going to be a t-test or interval. And there we go. We're using a t-distribution. So this, I will just bring this all up. If this is something you want to get a screenshot of, you can do that. This kind of shows the process for running through a one sample t-test. And of course, we didn't do the conclusion here, but my conclusion, just to verbalize it, would be because our p-value is still a p-value, we still call it that, because our p-value of 0.0039 was less than our significance level of 0.05, we reject the null hypothesis. There is convincing evidence that teenagers do not get 8 hours of sleep. They get less than 8 hours of sleep, specifically. Okay. All right. This is some serious stuff, guys. We've joked around, but now we're going to investigate something very real. You're beginning to think your life is a lie, and that the quarter pounder from McDonald's might not really be a quarter pound. All right. So you got to investigate this. And the name comes from the pre-cooked weight of the meat. So you investigate by getting a job there. And you sneak in a scale because you want to find out. So over the course of a week, you sample the uncooked weight of 100 quarter pounders and find an average weight of 0.240 pounds with a standard deviation of 0.18 pounds. Is McDonald's a factory of lies? All right, we got to find this out. I know you're not going to get any sleep until you know the answer. 8 hours. Oops. Yeah, you're not getting 8 hours of sleep regardless. All right. So let's investigate this. The first thing we need to do, and we don't have a lot of space to work with it, so I might have to do some work and then erase. First thing we want to do is decide what is our parameter of interest. Yeah, the true average weight of hamburger patty. At McDonald's. Okay, that's what we're trying to estimate here and make inferences about. What are our null and alternative hypotheses? Oops.
Our null is that the quarter pounder really does weigh a quarter pound.
All right, we're going to say that mu is 0.25. What's our alternate? Less than. We're not going to complain if they're giving us more than a quarter pound, right? Unless, yeah, Truth be told, I haven't had a quarter pounder and cheese in like 25 years, but not because I'm a better person than you. It's other reasons I'm better, but that's just something about me. Yeah, that's just one small part of what makes me better. All right, so we have a few things. We've got X bar. What's X bar? Let's go ahead and record all this.
Just go for it.
I believe in you. Point. You're off to a good start if you say point. 2.4. Yes, it is. I'm not going to worry about that point, that zero at the end. Okay. What's our sample standard deviation?
Oh, boy. I was thinking about the formula. The next thing for the formula is 0.25, right? Anyway.
I think that's supposed to be 0.018.
Yeah, there's no way.
Yeah, okay.
God.
Whoops. Let's go with 0.0 in it because that's crazy. Okay. Now let's also figure out what significance level we're going to do this test at. 0.05. We're not told to do any different. Is there anything else we need to know? Well, let's go ahead and write this. What's our sample size? 100. Maybe we can even do this. We know we're going to be working with it. What's our degrees of freedom? 99 degrees of freedom. All right. We're pretty well set up. Let's check. So what's our test we're going to run? If you don't remember the names, you can just describe it.
A T.
A T. One sample T test. Okay. So one sample T test. And here's where you might want to add at the end for mu. All right. Let's check our conditions. Was this random? Yeah, it did come from one restaurant, but since they get shipments that come in frequently, let's assume, yeah, it's random. Maybe it'd been better to go to a lot of different McDonald's. So maybe to do a real analysis, you need to go and work at a lot of different McDonald's. Okay. Second, is this meeting the 10% condition? Yeah. I feel like they've sold many billions of burgers and maybe they advertise that. All right. Third, is this, well, we say normal, but really not normal. Is it a T distribution? Like, yeah, our sample size is greater than or equal to 30. So we're good. Now we're really assessing normality, but it's not normal, if that makes sense, because we're using a T distribution. We're good to go on all three. Oh, we keep forgetting. There's nothing else on the next page. So let's go ahead and I'm going to erase the assumptions that we just checked. Are there any questions on this as I'm erasing? I just want to make sure that all the different steps we're doing, it makes sense why we're doing those particular steps. So now what we want to do is we want to calculate and actually do the math behind this. So we're going to do the test statistic is equal to the stat minus the parameter divided by the standard error. In our particular case, what is our test statistic? Like, what will I replace for our specific formula? So which one should I use, T or Z?
T, sorry.
T.
The stat, not the
right. No, and I get that. Yeah. So just remember, yeah, we are using a T statistic. Now we can jump to the other side. What is our stat? X bar. What's our parameter? Mu. And what's our formula for standard error? The sample size, yeah. And this is the sample standard deviation, which probably won't matter a whole lot except in a multiple choice question. If they're asking you a question and they give you two options that both look good, and one says sample standard deviation, one of them just says population standard deviation. Make sure it's the sample. Okay, now we can plug numbers in, and I'll do that over here. Our X bar was, well, we've got it right here. You know what? I'm not going to plug anything in. You guys do that math, and you will need to use your calculator or table B in order to figure out your p-value at the end.
That actually right?
That is, and just with rounding, mine's a little different, but that will happen, right? So an incredibly small p-value, I will tell you, typically with AP questions, they're not going to be that small of a p-value, because we did run into a situation where Leo's calculator was showing it as just 0. It was such a small number, they just said it's 0. So if that shows up, of course, that can be a problem. You don't want to report a p-value of 0, but the calculator tells you that. Anyways, very, very small. Now let's draw a picture to make sure we understand what this means, okay? And this is where I will erase all this stuff and give us some room up top. So with this, we have our, no, I want to do this. So I'm going to have a long tail over here. We have our distribution. All right, our mean that we are assuming to be true is 0.25. It turns out that our standard error for this distribution is going to be 0.0018. So let me just write this here. I'll just put the standard error off to the side. Is 0.0018. And with that, we're going to have to go all the way down to -5.5. So here's -1, 2, 3, 4, 5. I'll go ahead and draw the 6 on here. So we're living right down here. Our test statistic T. So that is where our test statistic is. We want to find the area of under the curve at that value or more extreme. So here's the p-value. And that's why the p-value is so low, because we're at 5.5 standard errors away from the mean. So at this point, do we reject or fail to reject the null hypothesis?
Rejection.
We reject that null hypothesis. So to verbalize what I might write down, because our p-value is less than the significance level, we reject the null hypothesis. There is convincing evidence that hamburger patties at McDonald's weigh less than a quarter pound. All right. So there we are. Oops. Sorry. Technical difficulties. There it is. So let me see. We only have one more example, and we can just run through this one, and maybe at a certain point, this is combining type 1 and type 2 error also. All right. So, okay, there was a question on how you find the p-value. Okay, and that's a good question. So let me go back to that last one. It was -5.55 as the test statistic. And we are looking for that value or more extreme. So this is where we use TCDF. So that is under the distributions menu. It's option number 6. And so we're going from a lower value of -99, because we're saying basically negative infinity, which -99 is basically the same, to -5.556 with a standardized normal modeler. I keep saying normal, technically it's a TCDF. We are also going to have, we also have degrees of freedom in here, which is, I apologize, I was using the stuff from a normal CDF. So we're going to have 99 degrees of freedom. My gosh, I can't get this right.
Why do we have 99?
Because there were 99 degrees of freedom. And, our sample size was 100.
Oh, yeah, you just minus.
Yeah. There it is. So there it is. So Turns out it's just punching some numbers in wrong, but there you go. So just remember, if you are finding the area under a normal distribution that looks like this, it's a normal CDF. If you're finding the area of a t-distribution which has slightly fatter tails, and I'm exaggerating it, you use t-CDF. All right, and in a one like we just did, it doesn't have any practical difference, but it can. Okay, so let's look at this example. Let's see what we can do with this. During an angiogram, heart problems can be examined via a small tube called a catheter threaded into the heart from a vein in the patient's leg. It just creeps me out thinking about it, but anyways, it's important that the company that manufactures the catheter maintain a diameter of 2 millimeters. The standard deviation is quite small. Each day, quality control personnel make several measurements to test the null hypothesis that it is 2 millimeters against the alternate hypothesis that it is not 2 millimeters at a significance level of 0.05. If they discover a problem, they will stop the manufacturing process until it is corrected. Is this a one-sided or two-sided test? Two. Why is it two-sided? Yeah, we're saying it's just not equal to. Okay, and in the context of this problem, why do you think that it's important to do it this way?
Because if the catheter is too big or small, it can mess up the angiogram on it.
Yeah, okay, there you go. So yeah, this angiogram depends on having it 2 meters. So too small, too big can throw it off in different ways. So this isn't actually a t-test that we're about to perform. It's just a question about type 1 and type 2 errors. Okay, so explain what happens in this context if the quality control people commit a type 1 error. So let's write, we already have the null hypothesis. I'm just going to write them down. So type 1 error. In this case, do we decide that the catheter is 2 millimeters, or we decide that the catheter is not 2 millimeters? Yeah, with a type 1 error, we reject the null incorrectly. So we decide that it's not 2 millimeters, even though it really is. And what happens if that is the case?
Then we gotta shut down the manufacturing process. The boss has gotta come over and measure it, be like, actually, 2 millimeters are fine, and you gotta restart everything, and he's all mad at you. Then you get fired, and then you go home, you're all stressed out. Your wife makes it.
And then you turn to alcohol, and yeah, I mean, it goes. Okay, so, well, maybe that story plays out, but here's what happens. In a type 1 error, you shut down the process for a little bit, you determine if there is a mistake, and you lose some time. But that's the consequence, right? And now in a type 2 error, in this case, you have failed to reject the null hypothesis. You say that it is 2 millimeters when it's really not. What happens here?
So, and then you give it to like the doctor's office and people an angiogram on someone, and they're putting this little thing in this leg vein, but it's actually like 3 millimeters, so it goes up into his heart and just rips open the aorta, all of the ventricles, and then you really get fired.
You goofed up, man. That's a big goof right there. Okay. Yeah, so I think between the two, losing a little bit of time in the processing, the manufacturing process, that is probably your better error rather than type 2. And you can see that it's turned out quite a bit that the type 2 error is worse in a lot of practical situations. I'm not saying that's universally true. It depends on the situation if type 1 or type 2 is better. But in the academic setting, if you're trying to discover links between things and you decide that a type 1 error, and you commit a type 1 error where you claim something is statistically significant, reject the null when really it's not true. In some cases, that can be considered worse if it's like if it seems like you are massaging the data or p-hacking or whatever so that you can get a statistically significant result. But anyways, that just some good review, hopefully. So I thought I had another practice problem up here. If you want to go through another problem with the one sample t-test for mu, I'm happy to find another example of that. We can go through it. At this point, that's all we've got. We're all caught up. On Monday, we're going to look through a little bit more dealing with type 1, type 2 errors, get a little more practice in. So if you have any questions, stick around. Otherwise, you can have yourself a wonderful weekend, and I'll see you on Monday.
Later.